the voltage across the inductor leads the current by an angle 90 degrees. Either ways we can say that the current flowing through the inductor lags the voltage across the inductor by 90 degrees, or the voltage across the inductor leads the current flowing through the inductor by 90 degrees. Leading means, that means this VL leads I by 90 degrees. Leading means if the vectors are rotating in this direction, this VL will be first here. That means this VL will move first, after that this current will move. That means this VL leads the current I. Next, in a pure capacitor, the current leads the voltage across the capacitance by 90 degrees, or we can also say that the voltage across the capacitor, in a pure capacitor, the voltage across the capacitor lags the current flowing through the capacitor by 90 degrees. That means lagging means it will be like this. That means it is lagging, it is leading. The voltage across the capacitor in a pure capacitor lags by an angle of 90 degrees with this one. The voltage across the inductor leads by an angle of 90 degrees. So this is the vector diagram or a phasor diagram for an RLC circuit. Under resonance condition, what happened here is this VL is equal to this VC. So in a phasor diagram I can represent it as this, like this. Means these two vectors are same. VL is equal to this VC. Now you see, we know that Z is equal to R plus J into XL minus XC. So if I multiply on both sides of this equation with I into Z is equal to I into R plus J into I into XL minus I into XC. We know that I into Z is nothing but it is the current into the impedance offered by the circuit. Means that is the voltage across this series connection. That is nothing but this voltage. So that is the total supply voltage. I can represent it as V. So this V is equal to I into R. So it is the voltage across the resistance, that is VR. So it is VR plus J into the voltage across the inductance VL, the voltage across the capacitance VC. Now this VL is equal to VC. Under resonance, VL is equal to VC. So under resonance, VL is equal to VC. So V equal to VR. So whatever the supply voltage that we are given, that we are given to this series RLC circuit, the total voltage will be appeared across the resistance, that is VR. So it is a total voltage V is equal to VR under resonance condition, and VL is equal to VC. Now let me find the power factor. Let me define the power factor first. So what is meant by power factor? It is a cosine of angle between supply voltage to the supply current. Here the supply voltage is V and supply current is I. So the cosine of angle between, cos phi is the angle between the supply voltage and supply current here. So I need to find the angle between the supply voltage and supply current. We know that this V is equal to VR. That means this VR is equal to this V. So it is a supply voltage and this is a supply current. The angle between the supply voltage and supply current is 0 degrees here. The angle, both are in phase. So the angle between this V and I, supply voltage and supply current, is 0 degrees. So the power factor. So before going to calculate this power factor, let me draw the phasor diagram under resonance condition. Under resonance condition, this VL and this VC will get cancelled to each other. So there will not be any component of VL and VC in the supply voltage. Only V is equal to VR will present. So I know that it is I, and this is V is equal to VR. So this is the phasor diagram under resonance condition. And the power factor is equal to, power factor is cosine of angle between cos phi, where phi is the angle between V and I. We know that from this phasor diagram, the angle between V and I here is 0 degrees. Now power factor is equal to cos 0 degrees. Cos 0 is anyway it is 1. That is unity power factor. Any circuit which operates under resonance, the power factor of that circuit is unity power factor. That you need to keep in your mind. The power factor of any circuit which operates under the resonance condition is unity power factor. That is the angle between the supply voltage and supply current should be 0. That is about this power factor. Here another power factor is unity. That's okay. Next thing here is under resonance condition. Under resonance condition, if you see this circuit, if you see this point where VL is equal to VC, here this concept is variation of VL and VC with respect to frequency. Here this is the VC and it is VL. We already discussed this concept. So here this point, at this point is XL is equal to XC. At this XL is equal to XC. That means it is the frequency at which it is a resonance frequency. It is nothing but the resonance frequency at which both VL and VC are equal. And if you see this, it is the supply voltage and this is the voltage at the across the inductor, and voltage across the capacitor is VC. Both are equal here. What I mean to say here is under resonance frequency, the voltage across the inductor or the voltage across the capacitor both are equal and they are greater than the supply voltage. This concept is nothing but voltage magnification. So finally what I want to say here is, in this series RLC circuit, voltage magnification will exist. So in series RLC circuit, let me in series RLC circuit, voltage magnification will exist. Okay, so that is about the finding of this resonance frequency. First point is finding of the resonance frequency. Next point is finding of the bandwidth and some conclusions we should draw under resonance frequency. XL is equal to XC, Z is equal to Z minimum, that is equal to R, I is equal to I maximum, that is equal to V by R, VL is equal to VC, and also that means these reactive components under resonance condition of any circuit, the reactive components should get cancelled. That is VL and this VC get cancelled here. That is VL minus VC is equal to 0, V is equal to VR. So these are the points. Whatever the formulas that I keep in boxes, they are important. So these points. Okay, power factor is unity power factor. Next thing is finding the bandwidth of a series RLC circuit. Bandwidth. Okay, so what is the bandwidth? Let me define the bandwidth here. So before going to define the bandwidth of a series RLC circuit, let me draw this current waveform. Let me draw the current waveform for a series RLC circuit. It is a series RLC circuit. For this, if you draw this curve between the current versus frequency, we have already drawn this current curve in the previous concepts. So how will be the current? So this is the current here, current versus frequency. So this current will vary like this. It is an inverted V curve. So this is nothing but it is the current at, we can represent it as I naught. On this point, this frequency is nothing but the resonance frequency, okay, at which XL is equal to XC. Whenever XL is equal to XC under resonance frequency, the current will be maximum. We have already seen this concept. Next, bandwidth. So let me draw a line here. This point, make a contact of this point. Let us project these points onto the x-axis or frequency axis. So this point is F1, this point is F2. Now this one, the magnitude of this one, as per the definition of this bandwidth is the range of frequencies. It is the range of frequencies for which the magnitude of the current is above the 70.7% of its maximum value. Let me explain here. So this is a, let me draw this RLC circuit here also. RLC. V is equal to Vm sin omega t. RLC is VR, VL, VC. Okay, current will circulate like this, I. Okay, so this current versus the frequency graph will be like this. Bandwidth, it is defined as bandwidth is the range of frequencies, frequencies. So here this is the bandwidth. Let me explain. Range of frequencies for which the signal strength, or the current value or in brackets signal strength current value in a series RLC circuit is above the 70.7% of its maximum value. So what is the maximum value here? So this is the maximum value. I naught is the maximum value. So it is 70. This portion is having the magnitude of the current above 70.7% of its maximum value. If I write it 70.7% of I naught. So this point, so above this 70.7%, 70.8, 80, 90, 100%, that is 100% means I naught. So this 70 points, that means the range of frequencies for which the signal strength is above the 70.7% of its maximum value. Its maximum value is I naught. 70.7% of its maximum value above. So this is the range of frequencies. So for these frequencies, this signal strength is above the 70.7%. That means this portion of the frequencies is nothing but the bandwidth. That is, so this one, so that is from here to here, this can be called as bandwidth. So in this portion, the signal strength is above the 70.7% of its maximum value. Now this 70.7% I can write as 70.7 divided by 100 is I naught. That is equal to, if I write it 0.707 I naught. This 0.707 is nothing but I naught by root 2. if you calculate 1 by root 2 value, 1 by root 2 value, if you calculate 1 by root 2 value, this value is 0.707. You'll get it. That means finally what I want to say here is this point is I naught by root 2. This is I naught by root 2. It is I naught. Now my intention is to find this bandwidth. So bandwidth, finally I can write it as bandwidth is equal to, from here to here, this can be calculated by subtracting this f1 from this f2, right or not? If I subtract this f1 from this f2, then I will get this portion here. So that is f2 minus f1. So this is the bandwidth. Or if you want to find it is in hertz, you can also find the bandwidth in terms of omega 2 minus omega 1. It is in terms of radians per second. Now how to find this bandwidth? So first you see, first you proceed like this. Under resonance condition, under resonance condition, what is this current? Under resonance condition, current is I naught, that is equal to V by Z minimum. We know that. And V divided by Z minimum value is R here. Just now we have seen this. So under resonance condition, the value of the current I naught is equal to V divided by R. Let me find the current at the cutoff frequencies. So here F1 and F2 are known as cutoff frequencies. I forgot to say that. Here F1 and F2 are known as cutoff frequencies. Okay. And F1 is known as lower cutoff frequency. F2 is known as upper cutoff frequency. Okay. Now at these cutoff frequencies, I want to find what is the value of what is the impedance. So at this resonance frequency, the impedance Z is equal to Z minimum, that is equal to R. We know that. At the cutoff frequencies, so that means at these cutoff frequencies, I want to find the impedance. To find the impedance, I am using the current equation. So at the cutoff frequencies, or that may be F1 or that may be F2. What is the current? I is equal to, we know that it is I naught by root 2. The current value is I naught by root 2. Okay. But actually my intention is to find the impedance at these cutoff frequencies. To find the impedance, we know that the actual formula of the current I is equal to V divided by Z. Where Z is let us consider Z is the impedance at cutoff frequencies. Okay. Now let us equate this current with this current, because this is an impedance at the cutoff frequency. So this is the current at the cutoff frequency. But actually the current at the cutoff frequency is I is equal to I naught by root 2. So let us make this V by Z is equal to I naught by root 2. And we know that this I naught value is V by R. So this is equal to V by root 2 into R. So this V and this V will get cancelled. So finally the impedance that we got by equating this at the cutoff frequencies, the impedance offered by the circuit, series RLC circuit, is root 2 into R. So this is an impedance. After finding this impedance at the cutoff frequencies, let us redefine this Z. What is Z here? For a series RLC circuit, the impedance is Z is equal to square root of R square plus XL minus XC whole square, that is equal to root 2R. Okay. So this XL and XC are defined at the cutoff frequencies, that you need to remember here. This is an impedance at the cutoff frequencies. So this XL and XC are the reactances at the cutoff frequencies. Okay. Now let us square on both sides. Squaring on both sides. What happens here? R square plus XL minus XC whole square, that is equal to 2 into R square. So this XL minus XC whole square is equal to 2 into R square minus R square, that is equal to R square. Now this XL minus XC whole square is equal to R square, or XL minus XC is equal to, if I take the square root on both sides of this equation, it is plus or minus R. So this is an important equation. Let us consider it is equation number 1. Now this XL and XC are defined at the cutoff frequencies. Now at lower cutoff frequency, we know that we already discussed that below the resonance frequency XC, so the XC is greater than XL. After the resonance frequency, XC is less than XL. So from here to here, XC is greater than XL, from here to here, and from here to, that means from here to here, from here to here it is XC is less than XL. That means the circuit is under capacitive in nature, it is in inductive in nature, because this capacitive reactance dominates the inductive reactance. This inductive reactance dominates the capacitive reactance here. So it is in capacitive nature, it is inductive in nature. So now this F1 is under this region, means XC is greater than XL. That means XC value is higher than the XL. That means here if you consider XL minus XC at the lower cutoff frequency, so that is F1 is in this region, so at the lower cutoff frequency XC is greater than XL. So this value XL minus XC value, it will be negative. Why? Because this XC is greater than XL. That means XL is less than this XC, so this value will become negative. So let us represent it equation number 2. Now at higher cutoff frequency or at upper cutoff frequencies, at upper cutoff frequency, F2 is the upper cutoff frequency. Here XL is greater than XC. That means XL value is higher than this XC value. So this difference XL minus XC, since this value is higher than this value, it will become plus R. So let us represent it is equation number 3. So after framing these two equations, let me rewrite this equation 2 here. XL is nothing but omega L, XC is nothing but 1 by omega C, that is equal to minus R. Since it was defined at lower cutoff frequency, it is omega 1 L, it is omega 1 C. So it is equation number 2, same equation. I am just rewriting this. So here also XL, it is defined at upper cutoff frequency, that is omega 2L minus 1 by omega 2C, that is equal to plus R. It is equation number 3. Just I am rewrite this equation like this by replacing this. Next, if I add these two equations, so what is my purpose here is I need to find the bandwidth. Bandwidth is nothing but omega 2 minus omega 1 or F2 minus F1. For that I am doing the manipulations here. So what that calculations here are, just equation 2 plus equation 3 implies, just I am adding these two equations. So omega 1L minus 1 by omega 1C plus omega 2L minus 1 by omega 2C. That is equal to minus R plus R. Both are will get cancelled here. So this is equal to 0. Now omega 1, if I take L as a common here, omega 1 plus omega 2. Here in these two terms, if I take minus 1 by C as a common, it is 1 by omega 1 plus 1 by omega 2. Now L into omega 1 plus omega 2 minus 1 by C into, if I take LCM of omega 1 into omega 2, it will be omega 2 plus omega 1, that is equal to 0 here. Now this L into omega 1 plus omega 2, if I bring this term to the right side, it is 1 by C into omega 1 plus omega 2 divided by omega 1 into omega 2. Now this omega 1 plus omega 2, this omega 1 plus omega 2 will get cancelled here. So finally omega 1 into omega 2 is equal to 1 by LC. We know that this 1 by LC or 1 by, I can rewrite it as 1 by root LC whole square. So 1 by root LC is nothing but omega naught square. So this is the resonance frequency equation. Omega naught is equal to 1 by root LC. So omega 1 into omega 2 is equal to omega naught square. So omega naught is equal to square root of omega 1 into omega 2. Or if I want to write it in frequencies, 2 pi into f naught is equal to square root of 2 pi into f1 into 2 pi into f2. These are the frequencies in radians per second, frequencies in hertz here. So it is 2 pi into f naught is equal to it is 4 pi square into f1 f2. So if I bring this 4 pi square out of this square root, it will become 2 pi. It is square root of f1 f2. It is 2 pi f naught. This 2 pi and this 2 pi will get cancelled. So f naught is equal to square root of f1 and f2. So here what I want to prove here is this resonance frequency is the geometrical mean of this cutoff frequencies, in radians per second or in hertz. So here the resonance frequency is the geometrical mean of the cutoff frequencies. This point you can understand here. So this is the geometrical mean of cutoff frequencies. So that is equal to resonance frequency. What is my intention? I need not to find these things here. What I have to find here is, let us consider this is equation number. I already considered that it is up to equation number 3. Now it is equation number 4. That is omega 1 into omega 2 is equal to 1 by LC. This equation is required for me to calculate the bandwidth here. Now the same equations, equation 2 and equation 3. If I subtract this equation 2 from this equation 3, that means 3 minus 2 implies 3 is this one, equation 3, that is omega 2L minus 1 by omega 2C minus omega 1L minus 1 by omega 1C is equal to R minus of minus R. So this will become 2R. So here if I take L as a common here, it is omega 2 minus omega 1. Now it is, if I take 1 minus 1 by C as a common here, it is 1 by omega 2. This minus into minus, it will become plus actually. So if I write it 1 by omega 1. Now L into omega 2 minus omega 1 minus 1 by C into, if I take this LCM as omega 1 into omega 2, it is omega 1 minus omega 2. That is equal to 2R. Now L into omega 2 minus omega 1. So just cross minus into this one. I can write as 1 by C into omega 2 minus omega 1. Just I am taking the minus as a common here. So instead of omega 1 omega 2, from equation number 4, This is equation number 4. Omega 1 into omega 2 is 1 by LC. Just I am substituting this 1 by LC. This C and this C will get cancelled here. From equation 4, I can write it as from equation 4. So this C and C will get cancelled. So it is omega 2 minus omega 1. So it is L into omega 2 minus omega 1 plus L into omega 2 minus omega 1. That is equal to 2R. So I can write it as 2 into L into omega 2 minus omega 1. That is equal to 2R. This 2 and this 2 will get cancelled. So omega 2 minus omega 1, that is equal to R by L. So which is nothing but the bandwidth here. Bandwidth BW is equal to omega 2 minus omega 1, that is equal to R by L. It is in radians per second. So this is the bandwidth equation. If you want to find the same bandwidth in terms of F2 minus F1, just I am rewriting this 2 pi F2. This omega 2 is nothing but 2 pi F2 minus 2 pi F1, that is equal to R by L. So F2 minus F1, if I take 2 pi as a common here, F2 minus F1, that is equal to R by L. So F2 minus F1 is equal to R by 2 pi L. So that is equal to R divided by 2 pi L. It is in hertz. So this is how we can calculate the bandwidth. Next thing here is calculation of the quality factor. So I found the resonance frequency for a series RLC circuit, and bandwidth, and the remaining thing here is quality factor. So the quality factor, I can define it as quality factor. This is represented as Q. Okay. This quality factor can be defined as, it is the ratio of maximum energy stored in the circuit divided by energy dissipated per cycle. So both are under resonance condition, under resonance. So this is the formula for finding the quality factor of any circuit. So maximum energy stored in the circuit to the energy dissipated per cycle. So for this series RLC circuit, I am finding this quality factor. So here the maximum energy stored in the circuit is half Li square. If you calculate it, it is the maximum energy stored in the circuit. Since it is maximum, this value of the current is Im square, not the RMS value. It is the maximum value, Im square. Energy dissipated per cycle. Energy dissipation will happen because of this resistance. So the energy dissipation is power into time. Power is equal to I square R. So time into time. I square RT is the energy dissipated by this resistor. So it is, since we are calculating the energy dissipated in the resistance, I need to use the RMS value here. IRMS square into R into time T. And we know that the relation between the RMS value to the maximum value in a series RLC, in a sinusoidal circuit, Im by root 2. For a sinusoidal waveform, this RMS value is Im by root 2. And also this time is the inverse of the frequency here. So where omega is the, it is the frequency in radians per second. So I can write it as half L into Im square divided by this IRMS is Im by root 2 whole square into R into, it is 1 by omega, inverse of this frequency time period. Since it was calculated under resonance condition, it is omega naught. So it is I can write it as half L into Im square divided by half into Im square into R into 1 by omega naught. So this half Im square, this half Im square will get cancelled. So finally what we got here is omega naught. If I bring to the numerator, omega naught L divided by R. So this is the quality factor. Quality factor Q is equal to omega naught L divided by R. And this can also be, we can write it as omega naught L is nothing but XL. Under resonance condition, XL is equal to omega naught L. That is equal to R. And we know that XL is equal to XC under resonance. So this quality factor can also be written as XC divided by R. XL is equal to XC. So XL is divided by R. If I multiply on both sides numerator and denominator with I into XL divided by I into R. So I into XL is nothing but VL, the voltage across the inductor. I into R is nothing but VR. So this VL divided by this VR is nothing but under resonance condition VR is equal to V. And this I into, if I multiply the same with if I multiply the I, the numerator and denominator with I, in this expression I into XC divided by I into R. I into XC is nothing but it is the voltage across the capacitance. It is VR, voltage across the resistance. So VC by V. So all are the formulas for finding the quality factors. Now let me write this equation once again here. So this is quality factor. So these are all useful equations. So either way is omega naught L divided by R, or XL divided by R, or XC divided by R, or VL divided by V, or VC divided by V. So these formulas we can use while we are solving the problems. Okay. Next thing, quality factor Q is equal to omega naught L divided by R. But we know that omega naught is equal to 1 by root LC. 1 by root LC into L divided by R. This L and this R here I'm writing. So the same expression I can write it as L into C into it is root L into root L divided by R. This 1 root L and this root L will get cancelled. So what I can write here is, it is 1 by R into square root of L divided by C. So this quality factor Q is equal to, I can write as 1 by R into square root of L by C. So this is the quality factor for a series RLC circuit in terms of the elements resistance, inductance and capacitance. And there are no units for this quality factor because it is a ratio, energy ratios. Okay, it is energy, it is also energy will get cancelled. There is no ratio, there is no units for this quality factor. And this quality factor can also be named as selectivity. This quality factor can also be named as selectivity. Okay. This quality factor can also be calculated from this phasor diagram. So how to calculate quality factor here is from this phasor diagram. So this is the phasor diagram for this RLC circuit. This is a phasor diagram. We already drawn this. Okay, it is a quality factor. So this is the phasor diagram for this series RLC circuit. So this quality factor can also be defined as the reactive component, ratio of reactive component to the active component. So what is the reactive component here? Reactive component is either VL or VC. Here VL or VC, both are same here. VL is equal to VC under resonance. So active component, so this is an active component, that is VR or V. VR or V, both are same here. That means I can write as VL by V or VC by V. The same thing I wrote here, VL by V or VC by V here. So what is this VL by V? VL is equal to I into XL divided by V is nothing but VR, that is equal to I into R. that is equal to XL divided by R, omega naught L divided by R. This is how we can calculate. Or we can also calculate this using this, that is quality factor is equal to VC divided by V, quality factor, that is equal to I into XC divided by VR, that is I into R. Thus this I and this I will get cancelled here, so it is XC divided by R. XC is nothing but 1 by omega naught C into R. So I forgot to write this quality factor here. So the quality factor I can also write as, normally the quality factor we can write as omega naught L divided by R, or I can also write as omega 1 by omega naught RC or omega naught CR. So either ways I can calculate the quality factor for any circuit. So for any circuit it is better to remember this reactive component to the active component, because in the parallel RLC circuit I need to use this formula to find the quality factors. So reactive component in the phasor diagram, either VL or VC, both are equal here, VL or VC divided by active component, that is VR or V. Next thing here is resonance in parallel RLC circuit. Resonance in parallel RLC circuit. Here in this parallel RLC circuits there are three cases. That is, in case number 1, three types of parallel circuits are there. This is a resistance and inductance, capacitances. If all are connected like this, then if you apply the supply for this, it is V is equal to Vm sin omega t, R, L and C. It is case number 1. So this current, it will circulate the current I. Some of the current is going like this, let us consider it is IR. Some other current IL, this is IC. It is case number 1. It is one of the parallel RLC circuits. Second case here is resistance, inductance, capacitance. Now we are applying some supply for it. That is V is equal to Vm sin omega t. It is another type of parallel circuit. So it is R1, it is L, it is R2, it is C. This is the supply current I. If you consider it as I1, it is I2. Another circuit here is another type of parallel circuits, we can call it as a tank circuit. So in this tank circuit, the supply is given to the combination of resistance and inductance in parallel with the capacitance. So this is resistance, inductance and capacitance. It is V is equal to Vm sin omega t. This is the current I. It is, let us consider it is, since it is inductance, let us consider it is IL, let us consider it is IC. It's the current flowing through the capacitance. So these three are the these three comes under the parallel RLC circuits. Okay, for these circuits I need to find the resonance frequency for it, resonance frequency F0 and the quality factor for it. Here the resonance frequency F0, here the resonance frequency F0 and quality factor. These two things I will find. Here I need not to find the quality factor, but because it is somewhat difficult to calculate the quality factor here, so we need not to find the quality factor for it. Next, so let me explain this circuit first. So parallel RLC circuit. So first circuit here is R, L, C, IR, IL, IC. This is the current I. It is the voltage V is equal to Vm sin omega t. Okay. So any circuit, if we want to find the resonance frequency for any circuit, not only this parallel circuit and series circuit, for any circuit, the procedure is same. What the procedure here is, if you calculate the impedance, after calculating the impedance, we need to make the imaginary part of that impedance should be equal to 0. In case of series RLC circuit, imaginary part of the impedance should be equal to 0. In case of parallel circuits, the imaginary part of the admittance should be equal to 0. Okay. We can also make the we can also find the impedance for this parallel RLC circuit. After finding the parallel RLC circuit impedance, we should make the that is imaginary part of the impedance is equal to 0. But it is better to calculate the admittance for the parallel RLC circuits rather than the impedance, because in admittances we can directly add the elements, but in case of impedances we need to use the formulas, that is equal to R1 R2 by R1 plus R2, that is parallel combinations. For this parallel combination I need to find one equivalent impedance, and again I need to use another that formula R1 R2 by R1 plus R2 to calculate the equivalent impedance offered by this circuit. So finally what I want to say here is, if there is a parallel RLC circuit, find the admittance and make the imaginary part of that admittance is equal to 0, so that you can find the resonance frequency. If it is a series RLC circuit, better to calculate the impedance and make the imaginary part of that impedance is equal to 0. From that you can get this resonance frequency. Here first I will write the impedance. What is the impedance of this resistance? ZR is equal to R. What is that? Next, ZL is equal to J into XL. ZC is the impedance offered by this capacitance, that is minus J into XC. YR is equal to 1 by ZR, where YR is the admittance of this resistance, that is 1 by ZR. So I can write as 1 by R, that is equal to G. Next, YL, that is equal to 1 by ZL, that is equal to 1 by J into XL, that is equal to, what is this? 1 by J is nothing but minus J divided by XL. Next, YC is equal to 1 by ZC, that is equal to minus 1 by J into XC. Minus 1 by J or 1 by minus J I can write as J divided by XC, because J square is equal to minus 1, J is equal to minus 1 by J. From this I wrote this one. Okay. Now if you find the equivalent admittance of this total circuit, so Y is equal to, Y is the total admittance of the circuit, that is equal to YR, just by adding all the admittances of each element, YR plus YL plus YC, I can find the admittance. So what is this YR? It is 1 by R. What is this YL? It is minus J divided by XL. What is this YC? It is plus J divided by XC, that is equal to 1 by R. If I take plus J as a common here, it is 1 by XC minus 1 by XL. Now it is 1 by R, anyway it is G plus J into 1 by XC is nothing but BC, capacitive susceptance BC. BL is inductive susceptance, where BC is capacitive susceptance and BL is inductive susceptance. Okay. Now we found this admittance, and we should make this imaginary part of this admittance is equal to 0, so that I can get the condition for resonance. From that condition we can find the resonance frequency. So under resonance BC minus BL should be equal to 0. So BC is equal to BL. We know that BC is nothing but 1 by XC. BL is nothing but 1 by XL. That is XC is equal to XL. What is this XC? 1 by omega C. What is this XL? Omega L. Since it is under resonance frequency, we should differentiate the resonance frequency with the normal frequency. I am indicating omega with omega naught. Now it is omega naught square is equal to 1 by LC. Omega naught is equal to 1 by root LC. So the resonance frequency for this type of parallel RLC circuit is same as that of the resonance frequency of the series RLC circuit. So this is the resonance frequency, and if you want to find F naught, it is omega naught divided by 2 pi, that is equal to 1 by 2 pi root LC. It is in hertz. So this is the resonance frequency of a parallel RLC circuit. Now here in this concept, let me draw the variation of here the variation. It is another concept not included in this parallel RLC circuit. Okay, I will explain this after some time. So you will remember up to here F naught is equal to 1 by 2 pi root LC hertz for a parallel RLC circuit. Next thing here, quality factor. So F naught and quality factor. Before going to find this quality factor, first let me draw the some of the concepts, that is what is that under resonance condition, some of the conclusions under resonance. This BC is equal to BL. Okay, BC is equal to BL, and BC is nothing but 1 by XC, that is equal to 1 by XL. If I multiply with V on both sides of this equation, V by XC is equal to V by XL. V is nothing but the voltage across this line. So V by XL is this is the current flowing through this inductor. V by XC is the current flowing through this capacitor. So V by XC is nothing but it is IC. V by XL is nothing but IL. So IC is equal to IL under resonance condition. But we know that I is equal to, from this, I is equal to IR plus IL plus IC bar. So I bar is equal to IR bar plus IL bar plus IC bar. From the KCL, Kirchhoff current law, I can write this current, sum of the entering currents is equal to sum of the leaving currents. So I bar is equal to IR bar plus IL bar plus IC bar. So I is equal to, it is IR plus this IL bar, I can write as IL bar is equal to, actually it is V divided by ZL. IL bar is nothing but V divided by ZL, that is equal to V divided by ZL is nothing but the impedance of this coil J into XL, that is equal to minus J into V by XL. So I can rewrite this one as minus J into, it is IL, where IL is the magnitude, where IL is equal to V by XL. Next, similarly IC bar is equal to, so IC bar, this is the current flowing through this, that is V by ZC. So V by ZC, this V by ZC I can write as V divided by minus J into XC. So 1 by minus J I can write as J into V by XC. So it is J into, it is IC, where IC is equal to magnitude, it is V by XC. So finally what I want to write here is IL bar is equal to minus J into IL, IC bar is equal to plus J into IC. So IL bar is equal to minus J into IL plus IC bar is equal to, it is J into IC. So if I take J as a common here, it is IC minus IL. So it is current. Under resonance condition, IC is equal to IL. So this total current I is equal to IR. But in case of series resonance condition, V is equal to VR. But here in case of parallel resonance, I is equal to IR and IC is equal to IL. These points you need to understand. And what is the power factor? To find the power factor, I need to draw the phasor diagram for this parallel RLC circuit. In this phasor diagram, I can represent this IR, IL, IC along with this I and this V. This V, I, IR, IL, IC. I am going to represent in a phasor diagram. So phasor diagram. So this is a supply voltage, resistance, inductance, and this is capacitance. R, L, C, it is V, it is I, it is IR, IL, IC. Okay. Now the voltage is same in all the elements. The voltage across this R is V, the voltage across the L is V, the voltage across the capacitance C, because all are connected in parallel. So this voltage I am taking in, I am taking it as a reference. It is V for drawing the phasor diagram. Okay, let me draw. Okay, V. Now, in a pure resistor, the current flowing through the resistance and the voltage across the resistance both are in same direction. So it is IR. In a pure inductor, the current lags the voltage. Here the voltage across the inductor is V. The current flowing through the inductor is IL. The current flowing through the inductor lags the voltage across the capacitor by an angle 90 degrees. Lagging means I should write like this. It is IL. And in a pure capacitor, the current flowing through the capacitor leads the voltage across the capacitor, that is V, by an angle 90 degrees. Leading means it is IC by 90 degrees. So it is 90 degrees. So it is 90 degrees. Okay. But we know that I is equal to IR plus J into IC minus IL. Under resonance condition, so under resonance, IC is equal to IL. So I is equal to IR. So this IC is equal to IL here. So I is equal to IR. So this is IR is equal to I. And this IC is equal to IL. Both are same. This symbol represents these two are equal. Okay. Now let me, if you want to find the quality factor. Now from this, before going to find the quality factor, power factor, first let me find the power factor. Power factor PF is equal to cosine of angle between voltage and current, supply voltage and supply current. Here it is, the supply voltage is V, supply current is I. The angle between supply voltage and supply current is, here it is V and I, both are in same direction. So the angle between supply voltage and supply current is 0 degrees. So the power factor here is cos of 0 degrees. So it is 1. So unity power factor. So this is the power factor. So any circuit, not only this parallel circuit, not only the series circuit or combination of any series and parallel circuit, any circuit which operates under resonance, that circuit power factor is unity. That you should keep in your mind. Next, quality factor. Quality factor Q. So this quality factor, we already defined it. This quality factor is the reactive component, it is the ratio between the reactive component to the active component. Here the reactive components are IC or IL, either IC or this IL, divided by this active component is IR or I. Now what is this IC here? IC is the IC is the current that is flowing through this capacitance, right? I can write as IC is equal to V divided by XC. The voltage across this element V divided by XC is nothing but IC, and IR, the voltage across the resistance divided by R, is nothing but this IR. So this voltage and this voltage will get cancelled, R divided by XC. Now this R divided by, what is this, 1 by omega C. Since we are calculating the quality factor at resonance, so it will be omega naught. So I can write it as omega naught CR. So the quality factor, one formula for finding the quality factor for a parallel RLC circuit is omega naught CR. And another formula, if I write Q is equal to IL by IR, and this IL is equal to the current flowing through this, that is V divided by XL. V divided by XL. IR is same, V divided by R. This V and this V will get cancelled, it is R divided by XL. And here R divided by XL is nothing but omega L. Since it is under resonance frequency, it is omega naught L. So quality factor can also be written as R divided by omega naught L. So these quality factors are reciprocals of the quality factors of the series resonance, series quality factors. Okay. Now here in terms of R, L and C elements, I am going to find the quality factor here. Q is equal to R divided by omega naught L, that is equal to R divided by omega naught is nothing but 1 by root LC. Quality resonance frequency for a parallel RLC circuit, it is L. This L, and I can read it as root L into root L. So this one root L, this one root L will get cancelled. So it is R into square root of C by L. So the quality factor for the parallel RLC circuit is R into square root of C by L. But in case of series resonance, series circuit, Q is equal to 1 by R into square root of L by C, just in reciprocal of this quality factor. Okay. Coming to the next circuit, that is before going to find the next circuit resonance frequency, let me explain the variation of this admittances for this parallel RLC circuit. Okay, I will explain this. Just you remember variation of G, BL, comma BC and Y with respect to frequency of parallel RLC circuit. Okay, you know that just now we found that it is G is nothing but it is reciprocal of this resistance YR. It is YL is equal to that, YR is equal to G, YL is equal to minus J into BL, YC is equal to J into BC. So here it is minus J into 1 by XL is nothing but it is BL. Okay, so where BC is equal to 1 by XC and BL is equal to 1 by XL. Okay, so it is minus J by XL, nothing but minus J into BL. Okay, similarly J by XC like this. Next, equivalent Y is equal to G, that is YR plus YL plus YC, that is equal to G plus J into BC minus BL. So if you draw the waveforms between frequency versus all this G, BL, BC and Y. G is independent of the frequency, it is not a function of the frequency. But BL is 1 by XL, that is 1 by 2 pi FL. BC is 1 by XC, that is 1 divided by 1 by 2 pi FC, that is equal to 2 pi FC. This BL and BC are the functions of the frequencies. G is not a function of frequency. First let me draw, this is the G here. G, this curve is G and this value is G here. Okay, it is not a function of even though you are varying the frequency, the value of G doesn't vary, it is independent of the frequency. Now BL and BC, it is as we already seen in the case of series RLC circuit, XL is nothing but 2 pi FL, XC is nothing but 1 by 2 pi FC. So this BL is in the form of XC, BC is in the form of XL. So these curves we are already drawn in the case of this series RL circuit. So XL will be like this. So here XL is analogous of this BC here because it is 2 pi FC. There XL is equal to 2 pi FL. So this is BC curve. And BL, it is like XC, that is equal to 1 by 2 pi FC. Okay, so it is like that one. So we already drawn that it will be, this curve will be, it is XC curve. So it is BL now, it is BL. And admittance Y is equal to, if you vary the admittance, then this curve will be at frequency 0. If you vary the frequency 0, at BC is equal to BL, this value is G. So this curve will be, as in the case of impedance, this curve will be like this. So this is Y, and this point, at this point only resonance frequency exists. So before this BC, I think BC or BL is greater than BC here. From here to here, BL is less than BC, because BL is at F is equal to 0, BL is equal to infinity, at F is equal to 0, BC is equal to 0. So BL is greater than BC up to this point. So this variation, you can understand this variation if you understand the variation of the resistance XL, XC and Z with respect to frequency in case of series RLC circuit. You try to read that. I already did a video on it, so you go through that video, understand that concept, so that you can understand this concept also. It is similar to that of that concept. Next circuit here is, this is another circuit of parallel RLC circuit. Let me draw that circuit here. That is second one. It is R L resistance and capacitance. Okay, it is R1, it is R2, it is L and C, and it is V is equal to Vm sin omega t. This is current I, this current is I1, this current is I2. Now in this circuit, what I need to find here is resonance frequency F0. How to find the resonance frequency? As I already told you, first we need to find the admittance. If it is a parallel circuit, first you find the admittance, then you make the imaginary part of that admittance equal to 0, then you will get the condition. From that condition you will get the resonance frequency. So first let me find this. First let me indicate the impedances first. So here F0 is equal to much. So Z1 is equal to the impedance offered by this branch is equal to Z1, R1 plus J into XL. Z2 is the impedance offered by this branch. Z2 is equal to R2 minus J into XC. Now Y1 is equal to, I know that it is 1 by Z1, that is equal to 1 divided by R1 plus J into XL. If I factorize it, it is R1 minus J into XL divided by R1 plus J into XL into R1 minus J into XL. This one and this one will get cancelled, same thing we will get here. So this is equal to R1 minus J into XL divided by R1 square plus XL square. So why I am factorizing it, after some time you can understand. Now Y2 is equal to 1 by Z2, that is equal to 1 by Z2 is nothing but R2 minus J into XC. So now it is again factorize it, R2 plus J into XC divided by R2 minus J into XC into R2 plus J into XC. This one will get cancelled, same thing you got here. So it is R2 plus J into XC divided by R2 square plus XC square. So this is Y2. Now the equivalent admittance or the total admittance of the circuit, of the given circuit, is Y is equal to, just by adding these two admittances I can get the total admittance Y1 plus Y2, that is R1 minus J into XL divided by R1 square plus XL square, plus Y2 is R2 plus J into XC divided by R2 square plus XC square. And separate the real parts and imaginary parts. Here R1 divided by R1 square plus XL square plus R2 divided by R2 square plus XC square. This is the real part, plus J into, it is XC divided by R2 square plus XC square minus XL divided by R1 square plus XL square. So this is an imaginary part. So to separate this real part and real imaginary part only, I am factorizing what is it, I am doing this process here. So now what is under resonance, this imaginary part of the admittance should be equal to 0. So under resonance XC divided by R2 square plus XC square is minus XL divided by R1 square plus XL square is equal to 0. Now XC divided by R2 square plus XC square is equal to XL divided by R1 square plus XL square. Here this point, XC divided by R2 square plus XC square, XL divided by R1 square plus XL square. I think this is the equation. XL divided by R1 square plus XL square. Alright. Now cross multiply it. XC into R1 square plus XL square is equal to XL into R2 square plus XC square. So it is XC is nothing but, what is this XC? 1 by omega naught omega C plus R1 square plus it is omega L whole square is equal to omega L into R2 square plus 1 by omega C whole square. Since it is under resonance condition, it will be omega naught. To differentiate the actual frequency with the resonance frequency, I am representing this resonance frequency with omega naught. Now just cross multiply it. R1 square plus omega naught square L square is equal to omega naught square into L into C into R2 square plus 1 by omega naught square C square. Now R1 square plus omega naught square L square is equal to omega naught square L into C into R2 square plus this omega naught square will get cancelled here. 1C, this C will get cancelled. So finally what we got here is L divided by C. And if I bring this term to the right side, then I will get here is that omega naught square LC to R2 square minus omega naught square into L square is equal to R1 square minus L by C. Omega naught square, if I take a common here, it is LC into R2 square minus L square, that is equal to R1 square minus L by C. So omega naught square is equal to R1 square minus L by C divided by LC into R2 square minus L square. Now omega naught square is equal to R1 square minus L by C. Just you take LC as a common here, LC R2 square minus L divided by C. So if you multiply it, the same thing we got here. So omega naught is equal to 1 by root LC into square root of R1 square minus L by C divided by R2 square minus L by C. So this is the resonance frequency in radians per second for this type of circuit. You should remember this formula for solving the problems. Now if you want to find the frequency in hertz, it is 1 by 2 pi root LC into square root of R1 square minus L by C divided by R2 square minus L by C. It is in hertz because F naught is equal to omega naught by 2 pi. Right. So for this type of circuits, this is how we can find the resonance frequency. Next thing here is another circuit. What is that circuit? This circuit, tank circuit. It is an important circuit. For this type of circuits, how to find the resonance frequency along with the quality factor. And also I forgot to draw the phasor diagram for this circuit. I forgot to draw the phasor diagram for this circuit. Let me draw the phasor diagram. So in this phasor diagram, I need to represent I1, I2, I and this V. So first, this voltage is common for this element and for this element. So I am taking this voltage as reference here. First take this voltage as reference. So this is the voltage V. Next, it is a RL circuit. In a pure resistor, this current and voltage are in phase. In a pure inductor, the current lags the voltage by an angle 90 degrees, but it is a combination of resistance and inductance. So this current lags the voltage by some angle. So I1. So let me draw this circuit here itself so that we can understand. This R1, L, R2, C. R1, L, R2, C. It is V, it is I, I1, I2. So V is taken as a reference. This current lags this voltage across. This voltage means this voltage and this voltage both are same. This voltage and this voltage both are same here. All the voltage is V here. So this current lags this voltage by an angle some phi 1. So this is I1 with an angle some phi 1. Now this current, it is a capacitance. A pure resistor, this current and voltage are in phase. A pure capacitor, current and voltage are current leads the voltage by 90 degrees, but it is a combination of resistance capacitance. So this current leads this voltage by some angle, that is phi 2. So this is the current I2. It is leading, this current leads this voltage by an angle phi 2. Now I can divide these components like this. So it is one component, this is another component, this is one component, it is another component. Here also this is one component, this one. Okay, if I want to find this, let us consider this sin phi 2. If I write sin phi 2 is equal to, suppose if it is O, A, B, some C, sin phi 2 is equal to AB divided by this OB, right? Sin phi 2 is equal to AB divided by this OB. But we know that OB is nothing but I2. This current is I2. So AB divided by I2. So AB is equal to I2 sin phi 2. This AB is equal to I2 sin phi 2. So from here to here, the magnitude value is I2 sin phi 2. Similarly, if I write sin phi 1 is equal to AC divided by OC. But this OC is I1, AC divided by I1. So AC is equal to I1 sin phi 1. So the magnitude from here to here is I1 sin phi 1. This is AC. Okay. Now I want to find this OA. If I want to find this OA, let us find the cos phi 2. Cos phi 2 is equal to this OA divided by OB. OA divided by OB. We know that this OB is I2. So OA divided by I2. So here now OA is equal to I2 cos phi 2. Now find this cos phi 1. Cos phi 1 is equal to this OA divided by OC. OA divided by OC. So OA divided by OC value is I1. So OA is equal to, same thing, right? So it is not OA, this point is A and this point is B. This is suppose D, because we can't say this point and this point both are same here. This is having one magnitude, this is having another magnitude. This point, if I project this, it is A. If I project this, it is D. It is OD. OD is equal to what is that? I1 cos pi 1. Okay. So here the reactive components, this is the reactive component. What is this reactive component? This reactive component is I2 sin pi 2, because I2 sin pi 2, this value. And this reactive component is this one, I1 sin pi 1. These two reactive components are equal under resonance condition. So under resonance condition, resonance condition, this I2 sin pi 2 is equal to I1 sin pi 1. And this current I is equal to, it is the summation of I1, what is that? It is OA plus OD, that is I1 cos pi 1 plus I2 cos pi 2. This is the current. And finally this current is I. This current I is equal to I1 cos pi 1 plus I2 cos pi 2. So this current and this supply voltage doesn't have any phase displacement, so that the power factor is cosine of angle between V comma I, that is equal to cos of 0 degrees, that is equal to 1 unity power factor. That is about the power factor and this phasor diagram of this type of circuits.